So welcome to this video with Animated Science. It's lesson 5, calculations of motion, that I just wanted to talk about for any students that have missed it. So it's a little bit about SUVAT equations, and it's quite high end. There's some difficult formulas to look at. Hopefully we can unpick that it's not as hard as you might think. So we're looking at SUVAT equations. So displacement S, U, initial velocity V, final velocity A, acceleration, and T, time, which is why we call it SUVAT, and they all have the same thing. Now we've got this tricky looking one here that you're given, and there's a less tricky one here, which is the acceleration formula, which I've just rearranged. I've swapped the T and the A round, so you can have it either way around. This is the same formula but rearranged, and this one is the one that really we're going to focus on, where time is not involved as a factor, which is really clever. So let's have a look at just a couple of ideas now. So SUVAT equations, people often are put off by it, but actually they're derived from some very simple ideas, and we're just going to look at this one, which is displacement found by looking at the average speeds, that's V plus U over 2 times T. Now the way we work that out is by looking at a velocity and time graph for a journey. So imagine that somebody is already travelling at initial velocity U, so it could be 3 meters per second. They accelerate up to a final velocity V, so it could be like 3 to 8 or something like that, in a time of a few seconds. Now hopefully you'd agree that for that journey the graph has got a triangular area and a square area. And if we think about the very simple formula, the most basic formula of distance over time is speed, so imagine a runner running a race. The distance they travel would be velocity times time, so the rate at which you're doing it, meters per second, how many seconds by, and that will give you your distance travelled. So all we do is we work out the square, which is U times T. We work out the area of the triangle, which is clearly the top bit's V, take away U, and we times it by T, and you get the triangle. Now the triangle plus the square is very simple. It's square plus triangle. Now if we do it algebraically, we can multiply out the brackets. This is this second line, and I get minus ut over 2. Now if you have a whole and you take away a half, you end up with a half. So I then get ut over 2, the vt over 2 is down there, I put the two together and I get this formula. Now luckily in the GCSE exam you're not required to do that, but I wanted to show you it because just give you an idea of all these formulas have not been magicked out of nowhere. They have just been very simply derived by looking at very simple ideas about motion. That graph you should understand, because you should be able to work out the distance travelled for a simple journey. Okay, now let's just have a look at what was in the book. So the Collins book that we use at school focused on describing motion, so we're looking at displacement, initial, final and acceleration as terms. Couple of questions. What's meant by initial velocity? It's just your starting velocity. It's a fancy word for starting. The final is just your final. What are the units? Well, the units are different. It's always meters per second squared. So if we look here at an acceleration, because it's the rate of change per second, so it's the speed, so meters per second, but it's per second, so every second you're changing. Now this formula, this v squared is u squared plus 2as. You don't have to derive it, you just have to use it. And the cool part is there's no time involved. So think about this. Car accelerates from 8 meters per second at a rate of 2.5 meters per second for 11 meters. We want to know what is the final velocity, so we use the equation as is. We substitute the numbers in, the 8 squared, 2 times the acceleration times by the distance or displacement, 11 meters. We add the two together, and we get 119, but that's v squared, so I've got to then root it, and then I quote it to two significant figures because everything in the question had two significant figures. So that's the most simple example, and like I said, you given the formula on the formula sheet, you just have to rearrange or apply it. Now this second one, you have to do a bit of rearranging. So train approaches a red signal with a speed of 10 meters per second. The signal then changes to green and the train accelerates. By the time it's travelled another 1,000 meters, it's now travelling at 20 meters per second. So the question is, what's its acceleration? Now we put all the numbers in, but the difference is to work out the acceleration, I do have to use proper algebra. So just like in GCSE maths, all we do is we move the u squared to the other side, so a positive becomes a negative, and then everything must get divided by twice the displacement, or the 1,000 meters. So I put all the numbers in, remember to put my squared bits in, and I work out the acceleration. So they're two kind of straightforward examples. That's sort of more foundation, very straightforward. This one a little bit more involved on maths because you've got to rearrange it, but it's just using simple times, divide, subtract rules for algebra, so it's remembering that skill from maths. Now the final one's a little bit more tricky, so we're looking at going into more like the sort of grade 8, grade 9 sort of question. So we've got to think about this. If we apply this idea to vertical motion, but where there's no air resistance, so they've made it quite simple for GCSE. If we think about gravity, it gives a falling object an acceleration of 9.8 meters per second downwards. But when a ball is thrown upwards, clearly it decelerates, so as it gets to the top of its flight, it goes slower and slower and slower and slower and slower, and then it stops, almost like it's on a cartoon. And then the acceleration will be equal to minus 9.81, and the acceleration will be negative. So then when the ball falls back to ground, the acceleration is positive 9.8 meters per second squared. So the equation can only be used when the object travels with constant uniform acceleration in a straight line. So let's look at how they might apply that. So the ball is thrown vertically at 16 meters per second. So ignoring air resistance and taking g as 9.8, calculate how high it goes. Well, we use the SUVAT equation, and we know u, and we know that v is 0, and that's really important, isn't it? It's not that it doesn't have a value, it is actually 0. We know what the acceleration is, but think about this. The speed or velocity is going up. Now the acceleration is acting as a negative against it, so we put it as a negative backwards. Now that makes our formula a little bit tricky. So v squared is 0, u squared was 16 squared. I've got the plus, now it's plus 2. Now the a is minus 9.8 and the s is just s. So I end up with a minus 19.6 s, 256, and I have a 0. So I move the 19.6s to the other side, and then I divide 256 by 19.6, and I get 13 meters. And again, I put two sig figures. This would be the most difficult calculation you would have. So hopefully today we've just had a little look through the calculations of motion, which is a little bit tricky, and we need to remember that s is displacement, don't confuse it with speed, and that the u is squared, and multiplication has to be done before addition. Then you take the square root to get v, and you notice we do two sig figures, which could be a marking point, especially for the higher candidates. And then it's also thinking about as well, if an object's slowing down, then v will have a smaller value than u, so you've got to take that into account. So video on calculations of motion.